So good day. I'm here to present the angular modulation. So my name is Andrew Chu, and so let us discuss what angular modulation is. So first, modulation is used to transmit information from one place to the distant places. So mostly, this technology are employed in wireless communication. So modulation can be divided into angle modulation and amplitude modulation. So, angle modulation is when the phase angle of a sinusoidal wave is varied with respect to time. So, while amplitude modulation, here the amplitude of the wave is varied. So, angle modulation allows for more efficient use of transmitter power and is capable of handling a greater dynamic range of modulating signal without distortion as occurs in AM modulation. So angle modulation can be divided into two types, which are the frequency modulation and phase modulation. So let us discuss it on the next slide. So first, frequency modulation. In this modulation, the frequency of the carrier signal is altered in proportion to the message signal, while the phase and amplitude are kept constant. So the frequency of the carrier wave is modified in order to send the data or information. So it cannot transmit over long distances and have a smaller range. And again, amplitude and phase remain the same. So as you can see here from the waves, this is the amplitude wave, which is the baseband signal, and followed by the carrier signal. And as you can see, the wave the frequency of the wave is modulated, while the amplitude and the phase are the same. So in phase modulation, in this modulation, the phase of the carrier signal is altered according to the low frequency of the message signal. So in phase modulation and frequency modulation, they are quite similar. But in phase, the frequency of the carrier signal is not increased. So the phase of the carrier wave is modified in order to send the data or information. So the same, the amplitude here is constant, and the frequency here is now constant, only the phase of the wave changes. So for amplitude modulation, it is a kind of modulation where the amplitude of the carrier signal is changed in proportion to the message signal, while the phase and frequency are kept constant. So amplitude modulation, or just AM, is one of the earliest modulation that is used in transmitting information over the radio. So transmitters and receivers are less complex than of FM or PM. So you can see the wave here. The amplitude is the one that varies as opposed to the FM, which is the frequency of the wave. So the comparison of the three modulation. Again, AM was the first modulation to be invented. So it was invented in mid 1870s. And FM was developed in 1930 by Edwin Armstrong. So FM and PM are quite similar. So just to remind, the amplitude and phase remain the same, while in PM, amplitude and frequency remain the same, and in AM, both the frequency and the phase remains the same. So the FM has a higher bandwidth with better sound quality. That is why we can see this being used for radio stations that provide music. So the frequency range of FM is 88 to 108 megahertz, and it's less susceptible to noise. As opposed to AM, it is more susceptible to noise, has poor sound quality, but can transmit longer distances. That is why we can see it being used by um, radio televisions and for news. So in PM, noise immunity is worse than FM but better than AM. This is used primarily for mobile communication or satellite communication like Wi-Fi and 4G. So some of the notable FM stations we have in the Philippines are here, like Love Radio, Easy Rock. So if you will notice their number, which is for Jam, it's 88.3. That's actually their their frequency range. So the lowest is 88.3 and the highest is 107.9, which is what we said earlier. So the range is from 88.88 megahertz to 108 megahertz. So for AM stations, here we have DZBB from GMA and DZMM from ABS-CBN and a lot more. So as you can see, their frequency is from 550 kilohertz and up to 1674 kilohertz. So for the FM and PM signals, with respect to their time domain, frequency spectrum, and mathematical equation. So for FM signal in time domain, this is the graph that is produced with respect to time. So as we can see here, we can say that the modulation can be increased so that the baseband variations can produce enough carrier frequency variation. We can see more clearly how the frequency of the modulated carrier continuously tracks the instantaneous baseband value. And FM is more intuitive than PM. There's a clear visual connection between the higher and lower frequency sections of the modulated waveform and the higher and lower baseband values. So here we have the PM signal in time domain. Um, so for the PM signal, the relationship between the baseband waveform and the behavior of the carrier is perhaps not immediately apparent. However, after a bit of inspection, we can see that the PM carrier frequency corresponds to the slope of the baseband waveform. The highest frequency section occurs during the steepest positive slope of X sub B double B, and the lowest frequency sections occur during the steepest negative slope. So here we have the FM signal in frequency spectrum. So for modulation index 1 and also modulation index 4. So for the single baseband frequency, M equals 1, modulation shown above, we have the following here. So a low frequency spectrum, including the negative frequencies, is translated to a band that extends above and below the carrier frequency. With FM, it is the spectrum of the integral of the baseband signal that appears in the band surrounding the carrier frequency. So here is the effect of increasing the modulation index. So from 1 to 4. So again, since frequency modulation and phase modulation are quite similar, it is not surprising then that PM's effect in the frequency domain is similar to that of FM. So for the mathematical equation for frequency modulation, here we have the equation, which is E sub Fm is equal to E sub C sine omega sub Ct plus M sub F multiplied by sine omega sub M times T. So here, E sub Fm is the instantaneous value of the Fm signal in volts, and omega c is the angular velocity of the carrier, which is in rad per second, or radians per second, and omega m is equal to angular velocity of the intelligence, which is also in radians per second, and m sub f is the modulation index, and E sub c is the peak amplitude of the carrier in voltage. So it is quite similar to the phase modulation, in which here we have now E sub Pm, which is the instantaneous value of the Pm signal in volts, and omega sub c, the angular velocity of the carrier in radians per second, and omega sub m is equals to the angular velocity of intelligence, which is radians per second also, and m sub p, which is the modulation index for phase modulation. So also, this is also the maximum phase shift caused by the intelligent signal. E sub c is the peak amplitude of the carrier, which is in voltage. So we can now have the equations for the modulation index, percent modulation for FM, the deviation ratio, and Bessel function for FM, and the bandwidth. So first, here we have the modulation index for FM. So for the modulation index is directly proportional to the amplitude of the modulating signal and inversely proportional to the frequency of the modulating signal. So therefore, for FM, the modulation index is expressed mathematically here, wherein M is equals to K sub 1 times V sub M over omega M. And it is unitless because the units will just cancel out. So M is equals to the modulation index, which is unitless, and K1 is equals to the deviation sensitivity, or the radians per second per volt, or radians per volt. So V sub M equals to the peak modulating signal amplitude in volts, and omega M is equals to the radian frequency, which is in radians per second. So for the modulation index for phase modulation, it is a bit different, wherein for PM, the modulation index is proportional to the amplitude of the modulating signal and independent of its frequency. The modulation index for a phase modulated carrier is expressed mathematically as M is equals to KVM in radians, or it is simply the change in the angle. So M is equals to modulation index and phase deviation. K equals to the deviation sensitivity, and V sub M is the peak modulating signal amplitude. So for FM percent modulation, with angle modulation, percent modulation is simply the ratio of the frequency deviation actually produced to the maximum frequency deviation allowed by law in stated percent form. So mathematically, percent modulation is equal to delta F actual over delta F max times 100. So delta F actual is equals to the maximum peak frequency deviation in hertz, and delta F max equals to the maximum modulating signal frequency in hertz, which is allowed by the law. So frequency deviation for FM, frequency deviation is simply the change in frequency that occurs in the carrier when it is acted on by a modulating signal frequency. The peak frequency deviation is simply the product of the deviation sensitivity and the peak modulating signal voltage, and is expressed mathematically as delta F is equals to K1 Vm in Hertz. So again, K1 is equals to the deviation sensitivity, and Vm equals to the modulating signal voltage. For phase deviation for PM, it is simply the maximum difference between the instantaneous phase angle of the modulated wave and the phase angle of the unmodulated carrier. The phase deviation expressed in radians is equal to the modulation index, wherein delta theta is equals to the peak phase deviation, and K equals to the deviation sensitivity, and Vm equals to the peak modulating signal amplitude. So for the deviation ratio, it is the worst case modulation index and is equal to the maximum peak frequency deviation divided by the maximum modulating signal frequency. The worst case modulation index produces the widest output frequency spectrum, and mathematically, the deviation ratio is equals to delta F max over Fm max, wherein dr equals to the deviation ratio, it is unitless. Delta F max equals the maximum frequency deviation in hertz, and Fm max equals the maximum modulating signal frequency, also in hertz. So Fm equation using Bessel function, one such identity of the Bessel function is shown here, and J sub Nm is the Bessel function of the first kind, of nth order with argument m, in which the modulation index can be rewritten as this. And when this equation is expounded, we will have this, wherein mt equals to the angle modulated wave, m equals the modulation index, vc equals the peak amplitude of the unmodulated carrier, j0m is the carrier component, j1m is the first set of side frequencies displaced from the carrier by omega m, and j2m is the second set of side frequencies displaced from the carrier by 2 omega m 2 omega m and J3m equals to the nth set of side frequencies displaces from the carrier by n omega m. So, to solve for the amplitude of the side frequencies, Jn, the Bessel function, can be rewritten as this. So, the exclamation mark there is the factorial, m equals the modulation index, and n equals the j or number of the side frequency. So, this is the table of Bessel function. It shows the Bessel functions of the first kind for several values of modulation index. We see that modulation index of 0 or no modulation produces 0 side frequencies, and the larger the modulation index, the more sets of side frequencies are produced. It can be seen that as m increases, the number of significant side frequencies increases. Consequently, the bandwidth of an angle-modulated wave is a function of the modulation index. So this graph here shows the curves for the relative amplitude of the carrier and the several sets of side frequencies for values of m up to 10. So it can be seen from the amplitude of both the carrier and the side frequencies vary at a periodic rate and resembles a damped sine wave. The negative values for Jm simply indicates the relative phase of that side of the frequency set. So for the practical bandwidth calculation for Fm, in an unpublished memorandum dated August 28, 1939, Carson established a general rule to estimate the bandwidth for all angle-modulated systems regardless of the modulation index. Carson's rule approximates the bandwidth necessary to transmit an angle-modulated wave as twice the sum of the peak frequency deviation and the highest modulating signal frequency. So this was called Carson's rule, and this equals to B is equal to 2 multiplied by the peak frequency deviation plus modulating signal frequency, and the unit is hertz. So delta F is the peak frequency deviation and Fm is the modulating signal frequency. So thank you. Here are the reference for this PowerPoint. So this was based on the book, most of it on the Electronic Communication Systems Fundamentals through Advanced by Wayne Thomasy, 6th edition. So thank you, and I hope you learned from the discussion about angular modulation. Thank you once again.